When we talk about SPI, today our lecture is about SPI, Serial Peripheral Interface, right? Um, it is one of the synchronous protocol, which is majorly used in connecting the microcontroller with the devices I have shown down there. Have you guys about these 1.8-inch LED? We will witness these things in our daily day-to-day life and the joysticks. So yeah, whenever the external controller we are using for the controller we are using the external joystick is the external game controller, right? You can see that, right? So we'll use these things in our day-to-day life. But between these two, the communication we may not witness in our day-to-day life because it's everything is in the wire, right? Coming to the SPI, it's a four-way serial interface. Every SPI, between every master and slave, there will be four lines. It will exist for all the time. So these four lines are slave select and master out and slave in. Master out and slave in the sense the master will send the data and the slave will receive the data through that line. And coming to MISO, there will be master in slave out, which means the slave will send the data and the master will receive the data whenever the master requests the data from the slave. So in the red color line, you can see here, right? This is the line in the red color box. These all are the pins of the SPI protocol. This is the SS in the sense of slave select and MOSI in the sense master out and the slave in, and MESO in the sense the master in slave out. SCK in the sense serial clock, synchronous clock also. So synchronous clock in the sense which this is the master. If it is connected to any of these things, if we are connecting this joystick, uh, this serial clock will be sent to this joystick so that uh, the joystick will think, oh, the master is calling me, so I need to respond according to the clock. Suppose, mm, one second. If it is requesting any data, so I have to respond according to that, or else if it is sending some data, so I need to process the data and have to produce the output. That is the way the communication is happening here. If we talk more about SPI, it's a four-way serial interface, and it was developed by the Motorola in 1980s. Before that, 1980s, we have low speed communication protocols like UART and I2C, and the I2C interintegrated circuit, which was designed by NXP. Now it is NXP, before it is Philips. So, why we have chosen SPI instead of these two protocols are already there. So we just want everything if we choose for the other thing when we are having something, so we'll go for some kind of advancements, right? So now here the advancements are like a speed. So with I2C, we can able to transfer some kind of speed roughly around 4 megabytes per second. So which is of very slow compared to the SPI. So with SPI, we can transfer the data up to 10 megabytes per second, which is like a 10 Mbps per second. So it's the maximum speed we can acquire through this SPI protocol. And coming to supports full duplex communication. Full duplex in the sense, now I'm talking, you people are listening, right? And your people are listening, you're just receiving the data. The thing what I'm speaking over here, you're just listening over there, and it's a kind of half duplex. Whenever you're talking to me and I'm talking to you, when we both are talking, you're receiving data, even I'm receiving the data. So it simply says that it's a full duplex communication. So two-way communication, we can come across the road. In the road, there will be one way, two way, like that is there. So one way in the sense half duplex. Only one-sided vehicles are going. Suppose if it is going to the north, only the north vehicles has to go on that road, and on the other way it has to be south. So it comes under half duplex. So whereas coming to the full duplex, two-way road is there. So one side, one north going vehicles are there, and the other side south going vehicles are there. So we can simply say that in the full duplex communication, there will be a two-sided communications are there simultaneously. So um, this is what the full duplex means. And whereas coming to it is a very loosely defined. So because there will be no frame, a bit frame structure, so we can transfer any data just simply like a start bit and a stop bits. And such kind of bits are no needed in the SPI protocol. But whereas in I2C, the bit frame structure will ruins our brain. Actually, we haven't discussed till now the I2C. If we can, if we have the overall idea about I2C, there will be some kind of bit frames. There will be some synchronization between the clock and the data bit will be there. So start bit is there, and after that, 7 bits of data will be transferred. Where in I2C, I'm simply saying about I2C, there will be 7 bits of data need to be transferred to the peripheral, external peripheral, which is like the address of the peripheral. That 7 bits of data simply says that uh, the address of the peripheral which has to be communicated with the master. So there will be some kind of a specifications within the bit frame. So start bit, address, and then acknowledgement in the sense, okay, when these address go hit the particular address, particular slave, the particular slave will give some kind of acknowledgement. Oh, I have attended the, like yeah, I'm ready to transfer the data and I'm ready to receive the data. That is what the acknowledgement will be given by the receiver to the sender. So after that acknowledgement bit, there will be the transfer of data. Actual what kind of data it's going to transfer, there will be like that. So this kind of a particular frame bit frame structure is there for the I2C. So these kind of things are not involved in SPI. So it is a very loosely defined. This is what I meant here. And often used for the data transfer between a smart controller and the less smart peripheral device. A smart controller in the sense we can transfer the data between the microcontroller, and this is the microcontroller. So between these two, this is the smart device. So this is a very less smart device. It's just motion controller, right? So we are just using the joystick to operate the gaming control over there in the screen. So we are just using, we'll consider this joystick as a less a smart device, and this microcontroller as a very smart device. So to make communication between these two things, we are using SPI, right? So as I have already told before, like the common applications of these two things are like SPI, or like we're gonna connect the displays like this 1.8-inch LED module, right? So with the we're gonna uh, connect this with the microcontroller and analog to digital converters and digital to analog connectors and the real-time clocks and gaming controllers, etc. So this is the real-time application of the SPI where we are using that. So when we more involved in SPI, so this is the construction of SPI. So there will be a master and there will be the slave inside the SPI protocol. So we have a few lines connected between, as I have already told you before, like there will be 4 lines which will be available for all the time. So these 4 lines will decide whether the master has to receive the data or like master has to send the data. So usually it is a low level, like uh, chip select is low trigger, right? Whenever whenever the device is not in function, it will stay always at the 5 volts. So active high in the sense. So the line will be always at the active high. Suppose if the master wanna configure any of the slave, so the time it will simply pull that active low to active high to active low, and makes the slave to enable to respond for the master. So it works like that. And SCLK, like a synchronous clock in the sense that to make all the slaves respond synchronously to the master. So, and coming to the MOSI, this is where the line wanna transfer the master wanna transfer data to the slave, and MOSI in the sense master out slave input. So I have already told you this before. Coming to MISO, this is a master in slave out. So where the data will be received from the slave to the master. Over here, the orange line indicates like that the data will be transferred from the slave to the MISO. So, and the more this is just a basic structure. So there will be more pin configurations are there. So we'll go when we work deep into it. So we'll come across them. So are you guys clear till the point? Guys, can you please respond?
Guys, you can ask doubts if you have any queries.
Yes, sir. Yes, sir. It's clear.
Yeah. Okay. Uh, I'll be respected to ask questions at the end of the session. So uh, anytime. Like if you wanna ask anything right at the moment, you can ask, and even if at the end point, it's okay. I'll be always respected to ask. So and the this is how the data is transferred. So here, as I have already told, right? So the chip select. So the chip select is there. So the chip select is always it is at a high level. So it is always stays at 5 volts when it is not working. Suppose if you want to configure any of the slave, suppose this slave it is calling. So that time and the master wanna transfer the data to this particular slave. So the time it will pull the active high signal to low. So the particular chip select line connected between these two master and slave will be pulled down. So it will be forcefully pulled down. So when it is pulled down, so the clock is also there. So the clock will synchronously send all the slaves. So the time the slave will respond according to the slave on the line slave select line. So whenever these two are correspondingly working, the MOSI in the sense a master of slaving. So the master will send the data to the receiver, which is slave here. So it will send the data, and if it is the master wants to receive the data from the slave, so the time the MISO will send the data, which is completely unidirectional. Like this is one direction and this is the other direction. So the MOSI will MOSI in the sense the master will send the data and the slave will receive the data. And in the violet line, you can visualize that the master will receive the data by sending data from the slave. So uh,
How
so
can we
serial
check acknowledgement here?
No, till now I haven't discussed about the acknowledgement. When we go deep into it, I'll just simply I'm just making you to understand clearly about these basic signals. So
Okay.
acknowledgement in the sense it will be detailed about that. So
Yeah.
yeah, whenever the slave receives the data, so in the bit frame, the slave will send the data kind of acknowledgement. So if it receives the data, it will send as a one to the master. So that time the master will think like, oh yeah, the data will be received by the slave. So that time it is it may came to the conclusion like the data is transferring successfully. So I need to send the rest of the data as well, right? So um, when we progress into more in detail, so that time I'll came to know, I'll make you know understand about that. So
Okay.
coming to the serial clock in the sense I have told you, um, synchronous clock or serial clock. So this is the one we need to understand very clearly because there will be two configurations. Maybe our clock will be ideal low or ideal high. This is by default, if we say ideal low, by default the signal is at low level. So if we want to activate the connection between the master and the slave, we need to make it high. So this level will be active high. So whenever the clock is high, which means that the slave and the communication between the master and slave is happening. So whenever the signal is low, all like sorry, if it is high, if it is at 5 volts by default, so it means that it is the ideal high, and by making it to the active low, the communication will be happening. So there will be two configurations in the clock, whether it is ideal low or ideal high. So it is very simple, ideal low or ideal high. If we configure them, uh, so here the clock is completely will be generated by the clock master. So the master will completely generate the clock, and there will be no significance for the slave to generate any kind of clock, because it has to respond according to the clock which was generated by the masters. It's simple as it is, right? So slaves do not require their own clocks even when they are transmitting the data. Suppose if any master requests the data, so the slave wants to transfer the data to the master. So the time there is no need of any clock need to be involved in the communication. So the slave doesn't have any sense at all of having clock. So it's simply a waste of power. So even if we can also do so by having clock for the slave, it's a matter of wasting power and all, right? So we don't need any clock between when we are transferring data from slave to the master. So usually the clock generated by the master will be in the range of megahertz. Megahertz in the sense 1 million samples per second. The clock with that range, the master will send the data of 1 million samples of data, 1 million bits of data. It's gonna send per second. It has that capability. So it's usually faster than UART and I2C, right? So that's the reason why we are using this. Uh, clock indicates when data should be sampled. I have already told, right? So clock is the one which gonna decide when the slave has to be sampled and when it has to read and when it has to write the data. And for each clock cycle, it will transfer 1 bit of data between the master and the slave. And clock can be ideal low or ideal high, as I have told, right? These are the two configurations they are available with. So it should be active low or active high, right? So uh, maybe anything we're gonna choose. So I'll make you clear in the next slide. So data can be sampled on rising edge or the falling edge. So suppose if the data is available at the master, it can be sampled any of the edge, either at the trailing leading edge or the trailing edge. This is called the trailing leading edge, and this is called the trailing edge. So maybe on this edge we can sample the data, or also we can sample at this data. So just to avoid the ambiguity and confusion, so we are using these two edges to sample the data. So whereas coming to master out slave in, so MISO line, which is like it is the line where we are transferring the data between the master and the slave. The master will transfer the data using this line. So there will be the chip select. So the chip select will whenever the chip select line goes down, when the master pulls the line to low, the time the master wants to make communication with the slave. So the slave will come in contact with the master, so that it will also transfer the clock. So the MOSI through this line, master out slave in, the data will be transferred to that particular slave, right? Hope you guys understand this point, right? Okay. Used to send the data from master to slave. Like there will be no need of whether we are sending the LSP or MSP. So we need to configure them when we are writing the code. So maybe we are transferring the LSP or MSP for the first time. So it's totally depends upon the style of coding we are doing over there. So the number of bytes depends on the implementation. So if we want to transfer 4 bytes or like 5 bytes or 7 bytes, any number of bytes will transfer when the chip select line goes down. So it's completely depends upon the way we are implemented. So chip select may be held low between the bytes. So when after 1 byte transfer, the next byte will transfer immediately, and the time duration between these 2 bytes transformation. So the chip select line will be always at low. So you can see here, this is the first bit it will be transferring to the receiver. So, and the second bit will be started at this point. So between these two these 2 bytes, in this duration of time, the chip select will be held low, right? Can you see? I hope you are seeing. So we have finished with MISO, right? So, and the next The next line is about the master and slave out. It's completely the vice versa case of the MOSI. So it's just like whenever the chip select line goes low, it's just asking, the master is asking the receiver, the slave, to transfer the data, whatever the data is available with you, just transfer the data inside you to me. So that is the point of main point of MISO over here. So used to send data from slave to master, and not all implementation, SPI implementation, use the MISO, because some of whereas in some particular applications we are just having the flash memories over there. So uh, flash memories and the LED screens are there. Whatever, if we are using only the LED screens are there. So the LED screens will just receive the data and process the data and just display on the screen. It doesn't send anything to the microcontroller. So the time there is no need of using the MISO line. So MISO in the sense the slave need not to be sending the data, right? So there is no need of using that MISO line. So in some applications we don't need of having these MISO line. So this is the point of MISO. And okay, till now, I think I hope you got everything. So maybe if you go through the slides, what I have shown before, you can get it very easily. So now the main concept lies here. So these are the additional topics in SPI. So this is the trick point lies here. So clock polarity and the clock phase, right? These 2 points are the which makes the SPI more specialized. So the combination of these two things will have end up with 4 modes of communication. Uh, so the next one is like clock polarity, as I have told you before. By mixing the clock polarity with the clock phase, we'll end up with the 4 kind of combination. So out of that 4 kind of combinations, um, we'll just choose any of the combination and we'll start having communication between the master and slave. So before that, I'll make it to clear about the clock polarity. So whenever the clock polarity is 0, it makes it simply we can understand like uh, it is ideal low signal, as I have told you before. Ideal low in the sense by default here it is the leading edge in the sense before the first rising edge or any of the edge, it is simply ideally low. So it is active high, but before the edge comes here, it is simply low. So uh, whenever the edge takes place, it is a high edge. So CPOL in the sense polarity of the signal is like a 0. So from 0 it is raising. So why I'm stressing here means in the sense you need to make it very clear in your brain. So the next point lies over here. So that's the reason why I'm stressing over here. So um, ideally low in the sense before the edge takes place, the clock is at a low level. So you need to make it very clear. It is at low level and before the edge. So ideally high in the sense before any kind of edge, whether it is raising edge or the falling edge. So the signal is at high. So just make clear, right? This is the leading edge. This is the first edge and this is the second edge. The clock polarity in the sense if it is a CPOL is equal to 0, ideally low signal. So the first edge gonna be rising edge here if it is a CPOL equal to 0. And when the CPOL is 1, clock polarity is 1, ideally it is at high level and it's gonna have the falling edge. So this is all about the clock polarity, and the next one is clock phase. Mm, Clock phase in the sense, um, have you guys about the phase angle in the waveforms?
Yes.
Phase angles, leading angle, lagging angle. Oh, okay, yeah, leading. Okay, like this is the raising edge, right? This is the clock we have shown before. So at the leading edge, at the leading and rising edge. So at this edge, the data is sampling over here, right? So uh, it means that clock phase is equal to 0. So whenever active low, CPOL is equal to 0 and clock phase is equal to 0. So which means that both are at 0. So the sampling is happening at the rising edge of the active high signal. So you can see here the SPI receivers may sample data on either leading or trailing edge or clock edge. So it may sample at the leading edge or it may sample at the trailing edge. So we have chosen the leading edge over here. So that's the reason the receiver will sample the data at the leading edge. So the time C phase is equal to 0. So when it is sampling at the trailing edge, because it is at the falling edge. So if it is sampling at the falling edge, which indicates that uh, the receiver will gonna sample the data at the trailing edge. So guys, the previous slide what I have shown you before and this slide, if you guys remember these two things, I'll show you the other thing in the next slide. So I have shown you before C polarity, like a clock polarity. When it is active low, it means that the ideally whenever the before starting it, the clock is at 0 level, and the phase in the sense it is processing the data at what stage? It is processing at the leading edge. So which means that with these two combinations, we can say that in the mode 0, in the SPI protocol, if we are using the mode 0 configuration, we are asking the protocol, the communication will be happening at active high, and the data will be sampled at leading edge, isn't it? So, whereas coming to the mode 1, you guys are not responding even. So, whereas in coming to the mode 1, clock polarity, here it is saying that it is active low, and the clock phase in the sense it is the sampling at the trailing edge, falling edge. So here it is at a low level, active low in these two stages. First two stages, it is at active low, and it is sampling at the leading edge, and it is sampling at the trailing edge. Whereas coming to the clock polarity, it is one initially. It is at one and it is falling. These one indicates this signal, right? So it is falling. So it will sample, the data will be sampled by the receiver at the leading edge, 0 in the sense leading edge. So uh, this is the point where it's gonna lead, right? So this is showing for the mode 3. I'm saying that for the mode 2. So if it is 0, this data will be sampled by the receiver at this stage. Okay. You can clearly see that here in the mode 3, the clock polarity is 1. So the clock polarity is 1 in the sense it is ideally at a high before the starting edge. So it is at high stage, and at the clock phase is 1, and so it is saying that okay, the protocol will sample. The receiver will sample the data at the falling edge. At this edge, the second edge, the trailing edge, the data is sampling by the receiver. This is what the modes of operation. So they have the flexibility of using these four modes. We usually go for the mode 0 because which is very suitable for any kind of application. So that's the reason we'll go with mode 0. We'll also use these three other modes to sample the data. So to avoid the ambiguity and confusion, we are going with the mode 0. So we have a lot of flexibility in designing that as well, right? So all SPI modes must be use the same mode. Suppose if we have four or five slaves connected to one single master, so to make communication between these slaves and the master, so we have to use any of four modes, but we have to use only one for all the modes of communication, right? So the configurations of the slaves in SPI. Guys, here you can clearly see that we have one master and we have three slaves over here. So if we want to connect these three slaves with this master, so the time, as I have already told you before, like there will be four lines in common, which is like a serial clock or synchronous clock, MOSI and MISO, and chip select. So these four lines will be there. So the chip select lines will be depends upon the number of slaves we are having. If we are having five slaves, so the time will be having with the five chip select lines. So it's totally depends upon the number of slaves we have. So the serial clock will be shared among all the slaves. So the line will be same common line. So first has been given to this slave, and then it will goes to this, and this is going to this. Whenever the clock, if the clock is generated by the master, it will be shared among equally across all the slaves. So it will be given all the slaves. So how to configure which slave? Suppose if I want to talk with these slaves, so there will be the chip select line too. So the master will will pull this active high line to low level. So this will go down. So it will ask with these two combinations. Like anyhow, we are providing clock to all these signals, all these slaves. So one second, guys. Okay. This chip select two line is there, right? So it will be pulled down so that we have the serial clock already it was there. So with these two combinations, when like we'll have a 0 1 combination, right? So the chip select 2 will go slow. It means that it's 0, it is at 0, and the clock is at high. So 1 0 combination based upon that 1 0 configuration will enable these particular slaves by using OR gate. Suppose if we have OR in that OR gate, if the two inputs are 0 and 1, the output will be 1, right? So the output will be 1, and it will enable these the slave to involve the communication between the master and the slave. So that's the way we configure here. This method of configuration is called independent slaves. So each slave will have their own particular chip select line from the master. Have you got it? So I hope you got it. This so coming to cooperative slaves, we have three individual slaves, but the connection between them with the master is completely different. You can see, right? So here a lot of complexity involved in connecting the chip select lines with the slaves. So whereas coming here, there are no more chip select lines. So we have only one chip select line, and it is sharing across all the slaves, right? So you can see that here the only one line is there, and the other line is directly connected from here. So there is no extra pin for the slave to. Just we have only one chip select pin for from the master, and the within the same pin we are having the other chip select line passing through the slave 3. So the connections are made accordingly. Like the serial clock will be shared among all the slaves, likewise in the independent slaves. So this is the slave clock line. So the same clock will be passed to slave 2 and slave 3 as well. And the MOSI line, master out slave in line, will be connected to MOSI here again. So this is the point, right? So we are transferring data from master to slave 1. And we are directly transferring data to this slave 1. So if you want to transfer any data between the slaves, the connection will be like here. MISO in the sense master in slave out. Suppose it has to transfer data here, and it has to transfer data from there to here, and it will transfer data to here, master. So it involves, it is in these cooperative slaves, every slave is cooperating for the connection between the slave and master. Suppose if this slave involves in the communication with the master, it will just simply receive the data from the master. But if it wants to send the data, it has to send data to slave 2, and then from slave 2 to slave 3, and from slave 3 to master. So there is a cooperative, there is a kind of some kind of understanding between the slaves, so that with that understanding, every slave is involved in the communication, so that the data is transferred between the slaves and to the master, right? So this is the way cooperative slaves and daisy chain process involves. So I would like to stop the session here because I would like to explain in the next session about the working of the SPI, like between the master and slave, there will be the shift registers involved. So how the clocks are making will enable these two registers using the clock. Um, so it will like that time we'll also discuss about the RTL design of the SPI protocol also. So this is the basic overview about this is just to make you to understand how the SPI protocol works. It's simply a protocol how the communication between the masters and slaves. Pin configuration simply, right? So hope you guys understand till the point. So if you guys not understand anything, please let me ask. I'll be respected to ask any question at this moment. So yeah. I'm gonna see who is there at the meeting. So who are the four participants? Mohan? Hello, Mohan.
Yes, sir.
Prince Mohan. Have
Hello.
you got any question?
Yes, sir. No, sir.
Yeah, you're free to ask anything, man.
I think so.
Hello.
Yes, sir. Hello.
Okay.
Hello.
Can you hear me?
Sir.
SK?
हेलो सर
Yeah. How you doing?
सर मुझे एक डाउट है इसमें स्लैब में आर यू कंफर्ट इन
Sorry?
हिंदी
थोड़ा थोड़ा सा इतना अच्छा
अरे,
हिंदी नहीं आता है भाई.
सर स्लैब में जो ये मीसो है लाइन है
एक मिनट. मैं
ब्लॉक
तो
डायग्राम जो
ये वाला.
यस सर
ओके. मैं क्या क्या बात है?
स्लैब में जो मीसो लाइन है इसमें जो डेटा है सर ये कौन सा डेटा है मास्टर का डेटा है या स्लैब का खुद का डेटा है इसमें जो
कौन सा?
मास्टर
कौन सा? मीसो.
यस सर
मीशो से क्या कौन सा डेटा ट्रांसफर होता है कि पता है? ये तो स्लेव है ना, इधर स्लेव. स्लेव के बारे में, स्लेव में थोड़ा थोड़ा डेटा होता है ना. तो पहले मास्टर सेंड डेटा टू स्लेव है ना. तो ये डेटा को सैंपल करने के बाद ये डेटा स्लेव पे रखा था. तो ये तो डेटा मीशो लाइन में बाद में डालता है. तो इसीलिए ये डेटा ट्रांसफर करता है. तो इसीलिए ये डेटा स्लेव स्लेव पे थोड़ा थोड़ा डेटा होता है ना, ये डेटा ट्रांसफर करता है मास्टर के लिए. तो मेरा हिंदी बहुत अच्छा नहीं, तो समझ में आए तो मैं
नो
तो
सर यू कैन कंटिन्यू इन
खुश.
इंग्लिश
ओके ओके. सो स्लेव में तो okay, I'll try to explain in English also. So the data, which is whatever the data is there, sent by the master to the slave to process and to process the data. So that it will process the data and store again it in the slave. So whenever the data process data inside the slave, whenever the microcontroller wants to process wants the data, so it will ask the slave to send the data back again. So that is the reason we are using MISO line here. So the sample, the processed data inside this slave one will be transferred through the line called MISO, master in slave out. The slave will send the data out and the master will receive the data here. That's the point of this line.
ओके
Any other doubts? Sanjay, Mohan Prince, and SK. Guys, who?
Okay. Still have any doubts or shall we close the session?
हेलो सर।
Hello, yeah.
सर एक साथ ही सारे स्लैब से कम्युनिकेट कर सकता है मास्टर क्या?
Sorry.
एक साथ ही ये जो तीन स्लैब है, स्लैब 1, स्लैब 2, स्लैब 3, इससे कम्युनिकेट मास्टर कर सकता है साइमल्टेनियसली?
Your voice is not very clear, SK. Can you put your mic towards your mouth so that you can get some clear voice?
हेलो सर।
Yeah. Now it is clear. Yeah. Please go on.
सर स्लैब 1, स्लैब 2, स्लैब 3, ये जो तीन स्लैब है, इससे मास्टर साइमल्टेनियसली कम्युनिकेट कर सकता है क्या?
Simultaneously, right?
यस सर।
Yeah. It's not simultaneously. ये तो simultaneous नहीं है तो क्योंकि हमारे पास तीन तीन चिप सेलेक्ट लाइन्स है ना, तो तीन चिप सेलेक्ट लाइन्स से अगर ए स्लेव 1 है, तो मेरा स्क्रीन दिखा दिया ना, तो स्लेव 1 है, स्लेव 1 से मास्टर बात करता है और मास्टर स्लेव 1 से बारे में बात करता है, तो इन बीच में स्लेव 2 के साथ बात करना चलता नहीं इधर, क्योंकि दोनों इन्वॉल्व है ना कम्युनिकेशन में। ये तो कोऑपरेटिव स्केड्यूलिंग है। इन दिस कोऑपरेटिव स्लेव, इसलिए ए स्लेव मास्टर से बात करने के लिए ये तो स्लेव 2 के बारे में बात के साथ बात करना, और स्लेव 2 स्लेव 3, and after slave 3 it has to go with master, right? So there is no point of involving these two slaves, slave 2 and slave 3 in the middle, but the slave 1 has to talk with the master, so that time it has slave 2 and slave 3 have to be involved for sure, because uh, directly the MISO line is going to the MOSI of a slave 2, and the MISO line of slave 2 is going to MISO MOSI of this one, and the output of this slave line is directly going to this master, right? So that's the reason. So in these cooperative slaves, the communication between these two lines are making indirectly, asking indirectly for the slave 2 and slave 3 involvement. So they have to involve for sure. Whereas coming to independent slaves, so in the master and the slave, the communication is of like one to one. So if you ask me, I'll say you. If I ask you, you have to talk to me. That's the reason. That's the point of communication. So when these two things are involved in communication, so there is no point of slave 2 and slave 3. But we are making only one chip select line low at a point at the time, so we are not enabling we are not disabling these two. If there all the time, they are active high. If we pull these two lines, these three chip select lines down, the time we are asking, the master is asking for the slave, please involve in the communication. So it won't do like that, because at a time there will be the communication between only 1 and 2, like the master and slave 1, or like either master or slave 2, or either with master or slave 3. That's it. But I have told you before, the full duplex, in the sense at a single point of time, when the communication is happening between the master and the slave, the single point of time, the slave and master can talk together. Okay. The MOSI and MISO lines are work simultaneously. The data will be transferred simultaneously between these two lines. Hope you got it, SK.
यस सर।
Yeah. Okay, guys. The next session will give you the update regarding the next session. So in the next session, we're gonna discuss more about the internal functionality of the internal function, the register functionality of the master and the slave, and then we'll discuss more about the RTL design of the SPI. So if you guys have any doubt, you can ask me or Prashanti anytime. So we are available all the time. So I think hope you guys understand and enjoyed the session. So if you have any questions and all, so please ping us on WhatsApp or any other place. So can we call it a day?
Yeah, thank you, Banu.
Yeah.
Yeah, thank you all.